Whenever we're doing a calorimetry problem, we're relating heat flows with temperature changes. And the first step in any problem like that is to set up the heat conservation equation that you're going to use. This is a master equation that determines how the rest of the problem is going to go. And it's going to be different for every system that you look at. Let's look at how you would set up heat conservation equations for certain systems. For example, sometimes when you've got semiconductor chips, you have an aluminum block next to the chip. So here's an aluminum block, and it's set up maybe on top of some kind of a semiconductor chip that you've got, say, in a phone or in a computer. And these things, since they have a lot of electrons flowing through them and they have some resistance, tend to get pretty hot. And this chip, when it's running, a computer chip, like a CPU or a chip in your phone, can get hot enough that the chip would actually burn up. It would actually get damaged if you didn't control the temperature of it. So they do that by putting some high heat capacity block that's going to soak up some of that heat, funnel it away from the chip as it's running, so the chip temperature doesn't get too hot. So it's pretty important when you're building a phone or a computer to know what's the heat capacity of the heat sinks that you're putting in there. So suppose we've got one of these aluminum heat sinks, and we measure its heat capacity with a little experiment. We're going to take, say, a styrofoam cup, which is a vessel that is pretty well insulated from the outside world. It is difficult for heat to flow across the styrofoam cup. And we're going to put some water in there. And what we're going to do is take a hot heat sink and we're going to drop it in there. Now, what we're going to do is collect some information, like what's the initial temperatures of these two pieces. And then we'll look at what the final temperature is, and we'll be able to figure out what the heat capacity of the heat sink is from that problem. The problem will start with making a heat conservation equation for this. Now, let's assume that the cup isn't part of the system, that we're just looking at the heat sink and the water to keep things simple. If I want to set up a heat conservation equation for this, the two things that I have in the system are the heat sink and the water. I'm going to have a heat that flows out of the heat sink if it's hot, and I'm going to have a heat that flows into the water if it's cooler than the heat sink. And I don't have to worry about what the signs on these are. That's going to come from their temperature changes later, but those all have to add up to 0. So that could be that heat conservation equation for my system here. Now, if I had some information about the cup, if I had any information about the cup in the problem that I'm doing here, I could include that as a component. And then my heat conservation equation would look like this. So you're looking at anything that can soak up heat or release heat in your system, and you're adding a term for that into your heat conservation equation. Now, what if I had, and this is a problem we're going to do a little bit later, a reaction running inside of a cup. So here's the cup. It's part of my system here. I have a reaction running inside here that's producing heat. I'm going to say RXN is my abbreviation for reaction. Now, I might have got that reaction started by mixing an acid and a base solution. So maybe I have a neutralization reaction occurring in here. And I also have a solution that the reaction is occurring in. So there are three components of my system here. The reaction is producing heat, the solution around it is absorbing heat, and the cup is absorbing heat. And I can write my heat conservation equation as Q solution plus Q reaction plus Q cup, and those things, in order for energy to be conserved, all add up to 0. Now, if I was naive about this, say I drew a picture that looked a little bit different. Suppose I had another cup up here and I had a base solution in here. And I'm dumping it into my cup where the reaction occurs. And I have my acid solution in here. So this is actually how I got this reaction to start. I dumped some base into the acid, stirred it up, and looked at the temperature change that was involved with that. I might think that the three components here are Q base plus Q acid plus Q cup equals 0, but that's not right. How do I know that's not right? Because it isn't the base that's producing heat or absorbing heat. It isn't the acid that's producing heat or absorbing heat. It is the reaction that is occurring between them that is producing heat, and the solution that they're in is absorbing it. So this part of the equation is not right because I don't really have heat sources and heat sinks in my equation here. What I am going to need is the actual thing that produces heat and the actual thing that absorbs heat in my heat conservation equation. So that's how I decide what goes into my picture or my heat conservation equation.